Now we have defined the probability space. Space as sorry, this is called the sample space. This is called the event space or the sigma field. This is called the T measure. Fine. And these definitions are, I believe, clear to you. The
Yes,
definition
sir.
and properties of these.
Yes, sir, it's clear.
Yeah. So we will list out a few more properties of the probability measure. So this is straightforward, and in a way we proved this yesterday. Sir, you want to say something? Sarit, do you want to say something? Ah, good. Right. And fine. Just a second. People say they are not able to join, so let me send the join link. Yeah. So this now define the probability of even conditioned on E2 as oh sorry, not this. Fine. This is how we define the conditional probability. So I hope this is okay till this point. Now the question is, where do we go from here? So therefore, if we have the knowledge of occurrence of event E, then infer the probability of occurrence of a related event F that probability that E occurs given that F has occurred. Sorry, probability that F occurs that E has occurred. F occurs that E has occurred is T of intersection F. Fine. This is okay. I'll switch to the chat.
Yes, sir.
Yeah, great. So we can say that probability of section F is, or the probability that E and F both occur is probability of E given F. Oh, sorry, probability of F given E times probability of E equals probability of F. Fine. So if we slightly rearrange these terms, what does this, what is this known as?
Bayes theorem.
Yes, Bayes theorem. So yeah. So probability of E given F equals probability of F given E, probability of E, and probability of F. Fine. So this is called the Bayes theorem. And what is just a second. I just remembered something. Just let me fish that out. I'll see that. See if I can copy PowerPoint slides. Yeah. So let's see if we can copy and paste PowerPoint slides here. Yes, we can. And yeah. So this, and let this picture load. It'll take a minute. Yes. So this is what so I believe a lot of you have watched this TV series, right?
Yes.
Yeah. So this is how this guy works, even in the books. So just a short poll. So how many of you have read the books? Just raise your hands to make life simple. Two people, three people, four, five, one volume. Oh, you have read the two-volume
The book
giant
for
edition.
book,
Yeah,
sir, book
sorry.
for book review or this book?
This book. Yeah, the books for book review is too early right now. So I believe around 5 or 6 people have read. And how many of you watched? Have you watched the TV series? 5, 6, 7, 8, 9. Just 10 people? No, 11 people.
So it's easier to watch movies
Huh?
than series. It's easier to watch movies than series.
The movie is not
See,
that bad. Series
the
is better.
books, the TV series, and the movies are all three totally different things. All three of them are good. This is not like Harry Potter where they take a good book and make it into a trashy movie, or Dan Brown books where they take an average book and make it into a trashy movie. The stories are
So has
good.
it ever
The
happened
huh?
an average so has it ever happened that an average book or a trashy book became an excellent movie?
Titanic.
Titanic. Had there been a yeah, I used to be a Dan Brown fan when I was your age. When I was 20 years old, I used to be a Dan Brown fan. And I used to be a Chetan Bhagat fan when I was 18 or 19. I would totally accept that. I have read Chetan Bhagat. Shoot me. Yeah. So anyway,
So he's good enough.
huh?
He's like okayish writer, not bad, not good.
Uh, he works on an assembly line principle. Or
Yeah, selling principle.
you read one of his books, that will be good. You read two of his books, you will get the hang of it. After that, it's just the same thing over and over again. There is nothing new. And that's my big problem with that guy. Otherwise, one or two books are good, depending on where you start. Anyway, let's not digress. So, uh, the key idea behind at least the series and the books, or the idea, the thinking idea behind the Sherlock TV series and the novels by the books, the stories by Arthur Conan Doyle, is that you observe the effect. You see that how likely is a cause to lead to that effect and how likely is that cause itself. Then you deduce that what was the cause of that effect. And this is actually is Bayes' theorem in practice. So this is where we use Bayes' theorem. And so my point is that this probability theory and Bayes, I don't know whether theorem aren't that bad. Fine, but you just need to be able to identify what are the causes and the effects. So anyway, we'll use a lot of Bayes theorem in the digital communications course. Hopefully I get to teach that. And if the knowledge of E2 or if the knowledge of E does not affect the probability of knowledge of occurrence of E of F, that is probability of F given E equals probability of F, then probability of F given E times probability of E equals probability of E intersection F equals probability of E times probability of F. Fine. And the events E and F in this case called statistically independent. Fine. Now, by the way, about this Sherlock TV series, the last episode aired the day I was offered a position at IIT Guwahati. Yeah. Now, probability of E equals probability of E given. So we can, there's a nice trick that we can use with this, that probability of E, I can write it like this, that you have two events E and F, then better write it mathematically. Probability of E equals probability of E given F, or I can rather write probability of E equals probability of E happens and F happens plus probability of that E happens and F doesn't happen. Right?
Sir,
Yeah.
so what you have written just above now?
The two events E and F in this case are called statistically independent.
Okay,
This,
independent.
yeah. Sorry, my handwriting turned out to be quite bad. I'll rewrite it for you. Fine. Or probability of E equals probability of E given F times probability of F plus probability of F complement times probability of F complement. This gives us another way of writing the theorem. So we can write now, right? So Bayes' theorem was probability of right. So we can write this as probability of this equals probability of f given E, probability of E, probability of f given E, probability of E plus probability of f given E complement probability of. Fine. This is okay.
Yes, sir.
Yeah. So have you done this before?
Yes. Yes.
Summation part.
Sorry.
This
Yes, in
summation part.
GE. Yeah.
So if you have done this before, then we can skip this.
Yes, sir. These things. Yeah, we have done.
Okay, this you have done. So you also know what are mutually exclusive events.
Yes, sir.
So I'll just write that E and F are called mutually exclusive if E intersection F is an empty set. Fine.
Yes, sir.
Yes, sir.
Yeah, Bhavnik, revision is always good, but I also have to balance the content of this course with so I don't want to spend unnecessary time on revising things that you already have covered in class. So from what I understand, since the lockdown happened or the lockdown started after your midsem exams, I reasonably would believe that the probability part was over, random processes was remaining.
Yes, sir. Like the distributions, only the basic ones were introduced, and we are okay with that. And
Yeah.
random processes
Even I
part,
would introduce the basic distributions, because the distributions that you would need to know are the uniform and the Gaussian, and the Bernoulli and Poisson for discrete. I believe you know all four of these.
yes, we do know this.
Yeah. So Bernoulli, Poisson, uniform, and Gaussian. These are the four distributions that I would want you to know, and so this is sufficient. Now, with this out of the way, let's come to the next big thing that I think I should clarify upon. Random variables, because yeah. So the question that I would ask is, because you have covered this earlier, so I would directly ask a question. Why is a random variable neither random nor a variable? Yeah. So I'll tell you this, that a random variable is neither random nor is it a variable. Now you can try to answer this.
Sir, it's just a mapping from the event space to real man. It's not a variable
Yes.
or a random.
Yeah. Yes. So a random variable by definition So is it's actually not from the event space, it's from the sample space. One thing.
Sir,
Map.
That's
Yeah.
right.
Huh.
sir, it can we understand that it's not a variable, but why is it not random?
I'll come to this. A mapping from the sample space omega to the real line and is generally denoted using capital letters from the English or the Roman alphabet. Such that random variable x is a mapping from omega to r. Fine. So now to clarify Shubhashish's question, let's say that we consider tossing of a coin. Fine. We consider the tossing of a coin. So omega now contains these. Omega is this. Fine. And x of h, I would say, is, say, heads is 1, fine. Shubhashish, these are okay.
Yes, sir.
So this x can actually take value 0 or 1. Now, whenever omega equal to heads, x of omega equal to 1, and whenever omega equal to t, x of omega equal to 0, fine. So this omega, the outcome is random, but the mapping of the outcome to the real line is, that is, for the same random outcome, I will always get the same number. So this is the mapping, the process that generates the outcome is random. The mapping of the outcome to the real line is deterministic. Bhavnik, can you please elaborate?
I mean that if we're mapping it to a real line, we're putting an ordering on them, right? Like tails is less than heads because heads is 1 and
No,
tails is 0.
you can always say that this is this I did out of habit. You can also say that x of h equals 5, x of t equals 100. This is equally valid.
That would still be a ordering, right? Like we're ordering them
Oh,
in a
okay.
way.
That way. Yeah, so that is kind this is a good question, and this is actually used quite a lot.
So, but it depends on the inference we draw from the distribution, right? If we
Yes.
don't want any ordering, we won't.
Yes, in general, we for the purpose of our applications in communication, this ordering is quite helpful. But yes, your question is good. So maybe you can figure it out and tell me the answer, or I will try to figure it out from somewhere, but that won't be easy for me or for you. But whoever figures it out, I'll let you know, or you can let me know.
Sir,
It's
assign
okay.
bonus mark.
You cannot tell me what to do.
So no, then the people will give more effort in finding this answer.
I want naturally interested people to do this. This is not something that everyone should know. I only assign bonus effort or bonus marks to things that people should know, or what is necessary for this course. What is for things like this, I assign chocolates. So I would say that whoever gets whoever answers this, whenever you guys come back, assuming that all of us are alive, at least I am alive, yeah, gets what? Amul fruit and nut, the big one, because I've
So it's a
started liking
promise,
dark
right?
chocolate. Ah,
It's a promise.
it's a promise. Fruit and nut, tropical
Okay.
orange. I
Okay.
have actually started liking dark chocolate, so I'm just naming off dark chocolates. You want a milk chocolate? I'll buy you a milk chocolate. Yeah, yeah. So actually, in the past semester, if you ask your seniors, in the past 2 semesters, I always gave out chocolates to the best performing students in the midterms and the end terms and the best project. So chocolates are always there. So
Then
fi whoever
we
finds
are at
out,
a,
huh?
we are at a loss then. We don't have
Yeah,
midsem.
yeah,
So
yeah, 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 yeah. So this is a way to compensate. So whoever finds an answer to Bhavnik's question, including Bhavnik himself, gets a chocolate. So yeah. So a random variable is, and for individual outcomes. So for outcomes. A random variable like the sample space is called continuous if its range is a subset of R, or a noun count, I should rather say it's an uncountable subset of R. Subset of R, a random variable is called continuous if its range can be mapped to a subset of Z. Fine, I'm not saying it's a subset of Z, but can be mapped to a subset of Z, just because we can have rational numbers as well. But rational numbers, the set of rational numbers isn't that convenient to think of. So yeah. Now we define the cumulative distribution function CDF of random variable as fx of x. Shrey, your speaker is on, so I got the notification for your email. Probability fine, this is small x, this is capital. Okay, so I'll just make the capital X a little more capital X like. So, Bhavnik, this is the point where that ordering comes into play. Shrey, can you please mute yourself? That would be helpful for all of us. I don't think he is hearing us.
So you can mute.
Just text him or something.
Sir, I guess you can mute him. You are the organizer.
Yeah, but then he won't be, if he wants to participate, he won't be able to unmute himself. Just he can text us possibly. Fine. So the CDF following varieties. One, again, two, which is non-decreasing function. Three, limit x tends to infinity fx of x equals 1. Limit x tends to infinity fx of, x tends to minus infinity fx of x equals 0. It is continuous from right, that is limit epsilon, better looking epsilon tends 0 plus f x plus epsilon equals fx. There's no such guarantee on it being continuous from left, because of this is because of discrete random variables. So you can see that in case of a discrete random variable, the CDF will be continuous from right and not continuous from left. right? So this 5 6 probability of a less than x, or the random variable taking values between a and b is 7 probability of x equals a equals plus.
Sir,
Yeah,
so what if fx is u of n?
fx cannot be u of n. Fx,
So
okay,
we,
fx is u of n. Then
yeah,
you, if fx is u of n, then you basically have it's not a random. It doesn't represent a random variable. It's a deterministic event.
okay.
Because if fx is u of n, which means that that event or the outcome is 0 with a probability 1.
Hmm.
So it's in that case it's a deterministic event, or it represents a deterministic event.
Okay.
PDF probability density function of so whenever I use the full random variable, I write of a random variable, and whenever I use the abbreviation RV, I write an RV, because R is R starts with the sound A. Ah. Yeah. Of a random variable is defined as fx of x equals d by dx. Fine. It has the following properties.
So doesn't this contradict the property that you stated it's continuous from right?
Doesn't what contradict the property?
So you stated it's not continuous from left, it's continuous only from right. But
Yes,
in order, but in order to differentiate, we require that it's both right limit as
you
well as
have
left.
a misbehaved function at your disposal for this. The Dirac delta function. So
Yes, sir.
if you talk about the continuous time unit step, right, that's why we call the step function and the Dirac delta function misbehaved.
Yeah,
Right. So the unit step also is continuous from right.
yeah.
And yet you define its derivative as the Dirac delta.
Okay, okay.
Okay. So both are these are misbehaved. Yeah, both of these are very misbehaved functions, and as we progress through uh, mathematics, or as we do harder and harder as we'll do more elegant mathematics, we'll try to avoid these as much as possible. But for third year, for a third year course, I believe we can get away with using the Dirac delta.
Hmm.
Has the following properties. random variable given as y equal to g of x, then fy of y equals probability omega such that g of x of omega less than equal to y. Fine. So this is a function of a function. Okay. So you have a class from 4, so I'll stop. And we'll continue on Tuesday.
Sir?
Yeah.
We, I mean, not in great detail, but we have covered some parts of these. Not from a mathematical perspective, but in our previous course.
Okay.
We had
Cool.
not
This
covered
is
random.
these are just then just treat these as so I won't be going into much details of these things.
Yeah, I think the random processes part was completely left out of our last course.
Yeah. So I'll
The
just
random.
what I'll do is, so my notes, what I've done is CDF and expectations and this two random variables and random variables and then random processes. Have you done and two random variables and random variables?
Yes, sir.
Okay. Cool.
Yeah.
So okay. So I'll just covariance.
Yes.
Yes.
Okay.
So, I mean, we can brush these topics
I'll just
once.
brush through these topics. So you might have noticed that I've increased the speed starting at so after Bayes' theorem, I've increased the speed. You might have noticed that.
Yes.
Yeah. So we'll brush through the other topics at this speed.
Okay, sir.
Okay. So we'll spend more time on random processes, but we'll just in order to just for the sake of completeness, we'll just run through the two random variable case and the multiple random variable case, and then start random processes. Okay. Okay, cool. So we'll do two random variables then. So it's 4 then. So I'll leave you.